All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are going back to the basics, I would say. Because for the past, I think, 1 or 2 days, I've been kind of revisiting the basics of PyTorch. It's not like I have advanced level knowledge in PyTorch. I still have very basic level knowledge. It's just that the the little knowledge that I had, I kind of want to refresh that because I had to step away from PyTorch for a little bit because I kind of got distracted with stuff like, scikit-learn and Hugging Face transformers and stuff like that. So I did plan on eventually getting back to PyTorch so I can learn how to build these various neural network architectures from scratch. And well, I'm doing that now. Hey, Qtane. Hello, hello. Welcome to the stream. Hold on. Appreciate the lurk. How are you doing, Qtane? I hope you're doing well. We are getting back to the basics with neural networks. I was yesterday, and I think the day before yesterday as well. I was kind of revisiting this section because here's the thing. Back when we were looking into this section, which is building the model, and this section, which is where we use AutoGrad to do to basically calculate the weights. AutoGrad is PyTorch's automatic differentiation engine, and using that, we are able to automatically calculate the new weights. We're able to automatically update the new weights because we are able to calculate the loss, and then we're able to change the weights with respect to the loss. So actually, well, yeah, what's really happening is we're calculating the whole with respect thing was more from calculating the gradients, and the gradients are calculated with respect to the current weights, and then based on those gradients, we update the weights. But yeah, anyways, autograd is used to calculate the not calculate the loss necessarily, but it's used to update the weights based on the loss. So we finished the autograd section as well. From what I remember, I don't remember if we got to the end of it. We never got to optimization. We also never got to save and load. So I pretty much only knew how to build the neural network. I didn't know how to save the network, saving the network and the weights. I feel like these are two separate things because I know the weights can be saved, but I need to see if there's a way that the network itself can be saved as well. One way is because I know that you can export this to the ONNX format, and in that case, yes, the entire network, the entire graph is going to be rewritten in ONNX in the ONNX format so that it closely represents whatever you were trying to build. But I think okay, you know what? Let's visit the save section. We're gonna go through this section because yesterday, or I think the day before yesterday, when I was looking through this, I kind of got hung up on one of the calculations because I like to try and do the calculations on paper or by hand, quote unquote, just to get an understanding of exactly what's going on there. I don't necessarily want to do all the math by myself, but I just want to get I want to get an idea. I want to be able to visualize that. Oh, hey, okay, this is what's going on. Even if I don't necessarily understand the math, uh, like in certain cases where calculus is involved, I may not necessarily understand the math, but I want to get a high level understanding. If I'm not able to understand the math, and if trying to understand the math is going to require me to go very deep into something like calculus, or if it's going to require me to learn something completely new, then I try my best to get a high level understanding of it. a conceptual, I should say, a conceptual understanding that, hey, you pass this input into this algorithm, and it gives you that output. And so and so and so and so is the behavior of this algorithm. So depending on what kind of input you give it, depending on what kind of values you give it, you're going to get different types of behavior from it. So I try to get, at the very least, I try to get that level of conceptual understanding, and that has been very helpful for me in various data science related situations where I don't necessarily always want to go too deep into the math. One, because I may not know certain math related concepts or certain math prerequisites that are required to understand that algorithm, and two, because I just don't want to spend the time learning that because it's not really going to benefit me. Like if I feel like learning the math behind something is really going to benefit me, then yeah, I'll put the time and effort into it. But if I feel like it's just going to be like if I feel like I can get away with using high level functions, then I try my best to just get a conceptual understanding of the thing. I don't try too hard to go deep into it. If I do try to go too deep into it, it'll be mainly for my curiosity. But anyways, I was revisiting the linear function. This is base. Wow, voice crack. This is basically what do you call it? It's a layer. This is a layer in a feed forward neural network, and I was trying to kind of refresh my knowledge. This is actually one of those things where I can do the calculation on paper because it's pretty much just matrix multiplication. So I was able to do the calculation on paper, and then I kind of got curious about how it is handling multidimensional data, and so I was experimenting with different values. Give me a second. Okay, yeah. So what was I saying? Yeah. So I was kind of confused about how it is handling. Actually, I think you guys are able to see the notebook, right? So let me just scroll down here. So I was doing some test calculations here. Passing in one-dimensional data is perfectly fine, right? If it's just like a flat array and that array has a bunch of values, as long as the number of values in there are the same as what the linear layer expects, you're good. But what happens when you what happens when you try to pass in multidimensional data? I wanted to find that out. So I was experimenting with different things. I tried passing in. Let me try to remember this example. So we have a 3 by 2. Yeah, I have this. I have the shape mentioned here. So we have a 3 by 2 tensor. So it's a two-dimensional tensor, and I was passing that in. I was passing that into this linear layer. The linear layer takes two in features and gives out four out features. Right. So I wanted to experiment with this in with various multidimensional tensors to see how exactly it was doing the calculation. And it turns out that so okay, when I this is one of those things where I'm just refreshing my knowledge because I've seen this before as well. It's one of those things where like it clicked for me before, and I just had to make it click for me again. So the thing here is it mentions in the documentation. Give me a second. This thing is being weird with the scroll. Okay, here. So it mentions this thing, right? The star here is basically whatever dimension, how many ever dimensions you want. and you're not limited to just two dimensions. You can actually have how many ever dimensions I don't know what the max limit is. I don't know if there is a limit, but you can actually give it multidimensional data. Uh, However, the last dimension is supposed to be the same number of features that this thing accepts. So what happens is the layer is going to take the entire tensor and it's going to run the calculations on the very last dimension, and it's going to return a tensor with of that exact shape. So when we talk about the last dimension here, let's say we are talking about, okay, so for the sake of understanding the example, we're going to keep the number of dimensions short. Let's say we're talking about a 3 by 2 matrix, right? This is a matrix with three three columns, and each column, no, with three rows, and each row has has two columns. You can see that here. A good way to sort of visualize it would be this, right? We don't have to call it columns and rows, but like calling it columns and rows kind of helps with the understanding. So we have three rows, and each row has two columns. So we are able to pass in two values into the linear layer, right? But we have three such rows. So what the linear layer does is it runs the calculations based on the last dimension. And so the last dimension is supposed to have the exact number of in features, and in the output you're going to get that exact same dimensionality uh, with the exact number of out features that you have specified. So in this case, I've specified 4 out features, and so you can see the result here. This is the result. So we pass in a 3 by 2 matrix, and so we also get back. Well, we don't get back a 3 by 2 matrix. We get back a 3 by 4 matrix because we specified 4 out features. So this was one of the things that I was trying to kind of wrap my head around, which is why I had to do the calculations on paper. I kind of have to remind myself that, oh yeah, okay, we can pass in multidimensional data, and it's going to operate on the last dimension, and it's also going to return the entire tensor with that same dimensionality, but with the last dimension set to how many ever out features you have. Um, where was I going with this? I forgot where I was going with this. Uh, I can't remember where I was going with this. Either way, okay. So we were gonna take a look at this. I think save and load optimization. I remember we had looked through optimization. It it was basically about optimizing parameters, and I think also optimizing hyperparameters. I think we did go through the section. I don't remember exactly, and I think it was in this section that they had introduced us to some kind of I think it was a library or a platform. I think it was a library that that kind of specializes in optimizing hyperparameters. I don't remember the name. It was I remember looking it up, and apparently it was a very famous library. So here we have hyperparameter tuning. There was some kind of library or some kind of program or something specified for it. Is it mentioned here, or do we have to go to the? Yeah, Raytune. That's what it's called. So at some point I have to look into this as well. I don't think I need to look into it right now. Once my knowledge in building neural networks becomes complex enough, or rather I should say, once I start building more complex neural networks, then I feel like it'll be important to kind of optimize the parameters. Though I I think I could try applying these optimizations to simple feed-forward neural networks as well, and see how it affects them. So I have okay. This is kind of interesting, right? We took a small, not a small, it was a pretty big. We took a detour and we started doing Hugging Face Transformers stuff, and through that I learned quite a bit, and there were quite a few concepts that were introduced in that, and because of that, now we're kind of converging back into PyTorch with various other concepts in mind. Stuff like, okay, basic, training a neural network from a network from scratch, but also, what was it called? Fine tuning. Yes, also fine tuning. So I wanna experiment with all of those concepts. I wanna build my own neural network, a very basic neural network, but then fine tune it, fine tune that very simple neural network and see how it affects things. I don't know to what extent I'm going to be able to do that well, given like very small amounts of data. Because like the silly experiments that I do in order to get a better understanding, I don't know if I'm going to be able to, um, I don't know if I'm going to be able to kind of successfully fine tune a neural network with with those experiments, because in those experiments always have I don't always have, what do you call it, I don't always have like a big data set to train on, and generally you require a lot of data, right? And when you're talking about fine tuning, you're usually talking about these models that have been trained on like massive amounts of very general data, and then you have to fine tune it on a considerable data set of, okay, give me a second, and then you have to fine tune it on a bunch of samples of the specific type of data that, how do I say this, you have to fine tune it um, for the specific task that you are trying to accomplish. But the fine tuning data set also has to have a considerable number of examples, right? So I don't know with my silly experiments to what extent I'm going to be able to successfully do that. I guess we can find out once I learn about fine tuning, because this is kind of an interesting concept. From what I understand, the idea with fine tuning, or the way that fine tuning is done, is that you freeze certain layers, and because you're freezing those layers, so their weights are not going to be they're not going to be changed when you do the back propagation. The weights are not going to be changed. So that's why you freeze those layers so that their weights remain exactly the same. But then you add a few new layers, or maybe even just one or two new layers, and those are the layers in which you're going to have your own fine-tuned they're meant to represent the data from your fine-tuned data set. I guess that's the best way to say it. So of course those layers don't have to be frozen, because you need to update their weights at each iteration. But as you're constantly running the neural network and then recording the loss and updating the weights, you're mainly only going to be updating the weights of these new layers that you've created, and so you're still able to use the old knowledge that the neural network had, because of which you're able to do a bunch of more complex things. You're not limited to just what the neural network was initially built for. Okay, so in terms of silly examples, something that I could do is, I mean, I have access to like a plethora of data sets on Kaggle. I could just go find a data set and use the data from that to do my silly experiments. Yeah, I guess I could do that. So I think, okay, the first thing, wait, we need to create a list here so that I'm able to keep track of all of this stuff. Right. So let's create a markdown list or a markdown cell. And so what are we looking to do? We need to first learn. Actually, I've already learned how to do it. I just need to. So okay, what are we trying to do? There's a couple of things we need to do here, right? One, uh, refresh knowledge of FCNNs. That's a feed-forward neural network, or in this case, I think it's fully connected neural network, which is referring to a feed-forward neural network. So refresh knowledge of FCNNs, then learn how to save and load the neural network. Oh, also, uh, saving model versus saving weights. I need to see the difference between these two. Okay, then what else? What else? What else? So after we've learned how to save and load the neural network, actually I don't know. I don't know what the save thing is teaching us to save. Is it teaching us to save the weights or the network or both? Because if we are saving the network means saving some kind of graph representation of it. Which, I mean, if we are exporting the model to the ONNX format, then yeah, sure, that makes sense. But I'm not sure how the network gets saved if you're just using some kind of PyTorch format. So here we have saving and loading model weights. Okay, saving and loading models with shapes. When loading, give me a second. Just a sec. Okay. When loading model weights, we need to instantiate the model first, the model class first, because the class defines the structure of a network. We might want to save the structure of this class together with the model, in which case we can pass model and not model.state dictionary to the saving function. We pass model, not model.state dictionary. So where do we pass model.state dictionary? Is that here? Oh, so these are the weights. Okay. So what exactly happens when you do this? We can then load the model as demonstrated. But what is this? How is this loading? Is it just loading it as some kind of like something similar to pickle, for example? It's called pickle, right? I think it's called pickle. There's a serialization format that allows you to save code and then run the code later. So it allows you to save Python code as in like a serialized format, and then you can load up that. So you first serialize the thing, and that allows you to store it, and then you can load it up and deserialize it and run it. Of course, this poses a security issue in that the code can be executed like that's the idea, being able to run executable code. So you kind of have to be careful of what exactly you are deserializing, right? But keeping that aside, is that what's going on here? As described in saving and loading, and wait, that was, oh, was that already described here? Where is it? Which section was this? Serialization semantics. Saving and loading tensors, and then modules. Okay, in PyTorch, a module state is frequently serializing. Is frequently serialized using a state dictionary. A module state dictionary contains all of its parameters and persistent buffers. Okay. Instead of saving a module directly, for compatibility reasons, it is recommended to instead save only its state dictionary. Python modules have a function, load state dictionary, to restore their states from a state dictionary. Okay. Right, but isn't like isn't the dictionary only going to contain all the values, all like the parameters and stuff? Even custom modules and modules containing other modules have state dictionaries and can use this pattern. I guess I don't understand what is being saved. Well, okay. So here we have, oh, you know what? Maybe the way that it's being saved, it kind of captures the relationship between them, and so maybe that's how it's able to reconstruct it. Um, you know what? Let's try asking Llama. Uh, okay. What was I talking about with Llama here? I think I was talking about fine tuning, right? Yeah, I think I was talking about fine tuning. Actually, I think here I was trying to have a conversation about something else. Oh, I also had an idea. I had an idea for being able to export the model, whatever the model might be from Hugging Face, assuming it's supported by transformers. I want to be able to export that to the ONNX runtime, to the ONNX format, and then run that in any program that supports the ONNX runtime. This way, I'm not limited to just Python. I can, for example, write a C# console program, and as long as I have an ONNX runtime running there, I can load up the model, run it, and use the weights as well. I want to try doing that with the more complex models. And fortunately, Transformers has a thing. I don't know if that's necessarily part of the Transformers library or if that's a separate library. But I remember, um, what was it? It was something to do with Optim or something like that. I remember that by looking at this. Oh, this is torch.optim. Okay, let me. What should I be looking? Oh yeah, okay. Transformers Onyx. Export to Onyx. Okay. Was this the thing? Deploying? Yeah, yeah. Okay. So what was the optimum? That's what it was called. It was called optimum. So Transformers has a thing called optimum that lets you export these models to the Onyx format. And something that I want to do is try, and this is going to be like much later, once I know how to train models. What is going on with my speech? Once I know how to train models, fuck's sake, dude. Give me a second. Let me hydrate. Actually, no. I think I can wait because I'm gonna have to step away in about like a minute and a half because I'm cooking some food. I need to go check up on the food, and I also, well, there's gonna be an ad break, so basically I'm just gonna do ad break stuff during that time. Hydrate, get up, walk around, and of course go check on the food as well. But yeah, okay. So at some point later on, once I'm much more well versed, I guess you can say, in training neural networks and also fine tuning neural networks, then I want to try doing something like this where I'll fine tune a model on a specific data set to accomplish a certain task, and then I'll export that model to the ONNX format and run it in either in a Unity app using their ONNX package, or actually, what was it part of? I think it was part of the Centis package. Yeah, I think it was part of the Centis package. So yeah, either run it in a Unity program using their Centis package, or run it in a C Sharp console app using us. I'm sure I'm sure there are ways to run the ONNX runtime. I can't remember what the library was. There's actually multiple libraries that allow you to do it. I don't know if I'm sure maybe Microsoft has their own library as well, because they had an ML.NET thing. I haven't explored that, but maybe through that I might be able to run it in the ONNX runtime, or I'll have to find some other way to get the ONNX runtime running. Okay, so I'm gonna switch to the BRB screen because um, I need to step away for a couple of minutes. I'm gonna go check on my food and then hydrate as well. And there's gonna be an ad playing in like, well, 15 seconds. So I'll see you guys in a couple of minutes. All right, I'm back. So where were we? I was gonna ask. Llama about. Okay, yeah. So I'm learning about PyTorch, or I'm learning about building NNs with PyTorch. NN is neural network with PyTorch. Um, I know that the model's weights and biases. Where's and did I not type? Okay, the model's weights and biases can be saved, but how exactly do we save the model itself, and in what format does no? How do we how exactly do we save the model itself, and how do we maintain the model's structure in a serialized format? Okay. All right. So when working with PyTorch, saving a neural network model involves more than just saving the weights and biases. You also need to maintain the model's structure. Here are different ways to save and load a PyTorch model, ensuring that the model's structure is preserved. Saving the model's state dictionary. This is the most recommended method because it provides the most flexibility when restoring the model. Okay. This contains the learn parameters, okay, and then loading is this. This method ensures the model's structure is defined by the class. Okay, so I'm kind of getting an idea of like I'm making assumptions here. Where's that saving page? So I'm making an assumption here that where exactly was I'm making an assumption here that this naming convention, this naming scheme, is how the model how PyTorch is able to then reconstruct the entire neural network. I'm guessing this naming scheme is how it's able to reconstruct the neural network, but I still kind of want I still kind of want to ask Llama if this is exactly how it's done. So I'm going to try and I'm going to try and prod a little for information. Create an untrained model instance. Models.vgg16. Oh, you know what? Yeah, at some point I should also take a look at the pre-made models that are provided by PyTorch. Not necessarily the weights. I mean, they'll probably provide the weights as well, but like pre-made structures that are already built, and you just need to load them up using PyTorch, and then you can either load your own set of weights, or you can load their weights and then retrain it and fine tune it or whatever. Dude, I love how sophisticated neural network stuff is because you're not limited to just one thing, right? There's okay, so you have a neural network. The neural network has a certain structure, right? It has what we call an architecture, right? You don't need to build the entire thing from scratch. There's plenty of other architectures that are made by much more knowledgeable people, and more importantly, much those architectures have been much more tried and tested for their performance, right? So you know that those architectures work well, but you can still build something from scratch if you absolutely need to, or if you just want to do it for the sake of learning, you can still do that. But you have the option to use ready-made architectures. So then you've got the architecture on one hand, the structure of the network on one hand, right? But then you've also got weights and biases. There's multiple different types of sets, I guess you can call them. There's multiple different sets of weights that you could use for one given neural network, and it's going to perform in different ways depending on the kinds of weights that you give it, because those weights represent the relationship between the input and the expected output. So you can kind of change the way that the neural network is going to behave depending on what kind of weights you give it. Not only that, given a specific set of weights, very generalized weights, you can then fine tune the neural network. You can change the neural network structure a little bit and then fine tune that neural network to operate on to do very specialized tasks through fine tuning, basically. Like I love how complex everything is. Not complex, sophisticated is the word I should be using. How, I guess you can say modular, because how customizable a bunch of these different things are. I don't know. It's kind of cool to me. Maybe it's just because I'm new to neural networks that I find all of this exciting, and I'm excited to explore more of it. But yeah, it's kind of cool. Okay, so saving the model's state dictionary. That was the first thing, right? Loading. Okay, this method ensures so saving the entire model. This saves the entire model, including the structure, using Python using PyTorch's serialization. You can save the entire model using torch.save. What was the old thing using? Save. That's also using torch.save, right? Oh, but in this case, you don't pass the dictionary. You pass the entire model itself. However, this approach has some limitations as it relies on the exact class definition being available when loading the model. This can make the code less portable and more prone to breaking if the model class changes or is moved. Okay, so wait, I don't get it. So what structure are you saving exactly if you still need the class definition to be present? All right, saving multiple components. If you need to save additional components like the optimizer, state, scheduler or epoch, you can organize them into a dictionary. Yep, that makes sense. Oh, I actually didn't think about this. I didn't think about just passing a dictionary to it and then having it save it in whatever serialized format it saves. Okay, this approach allows you to save and load multiple components of your training setup, ensuring that you resume training from where you left off. That is convenient, actually. No, that is super. Hold on, dude. I need to remember this because this is convenient because this allows you to pause the training, if I'm understanding correctly, because it says resuming training from where you left off. So I'm guessing that this allows us to essentially pause the training and resume it at a later time. Okay, best practices, state dictionary, so and so, so and so, so and so. Okay, so two questions I'm gonna ask here. I don't understand how the model's structure is being maintained when we save using the state dictionary. Looking at the values, it just seems like the weights and biases are being stored. How does PyTorch know what the structure. So I kind of have an idea. I'm just taking a guess. It's based on that naming convention that PyTorch knows how to reconstruct this model, but I still want the answer from Llama, just to just to kind of confirm. How does PyTorch know what um how does PyTorch know shit, I lost my train of thought. How does PyTorch know what the structure, okay, what the structure of the model is supposed to be when loading this data? Okay, so this is showing an entire convolutional neural network. Okay, when using the state dict method, the state dictionary to save and load a PyTorch model, a model structure is not directly stored in the state dictionary itself. Instead, the state dictionary contains only the learned parameters, the weights and biases of the model. Here's how PyTorch handles the model's structure. The structure of the model, including the types of layers, their connections, and overall architecture, is defined in the Python code that creates the model. This code is typically written using PyTorch's so and so and its subclasses. When you save the model's state dictionary, you are saving a Python dictionary that maps each layer to its parameter tensors. The file contains the learned parameters but not the model's architecture. To load the model, you need to have the exact same model definition. Oh, okay. Model definition. Here's how you load the state dictionary into a predefined model structure. So and so maps the parameters back to, okay, right. So what I'm getting from this is that in order to load, uh, in order to load a model, you need to have, what am I trying to ask? You need to have, oh yeah, you need to have the class, i.e. the structure, already defined in your Python code. What I'm wondering is there a way to store or to save a model in a portable format so that it can be, so one solution to this is ONNX, but I want to see if there's like a PyTorch specific solution. So you're not converting it to a different format. You're just saving it in a way that PyTorch is going to then be able to, you know, load it up again. What I'm wondering is there a way to save a model in a portable format so that it can be loaded by other Python code without the model's structure needing to be explicitly defined. Did I spell that wrong? Ah, explicitly defined in the Python code. Uh, Okay, let's see. So one solution to this is ONNX, right? But I want to see if this if Llama gives like some other solutions. Okay, Torch script. There's Torch script, and there was also something called Dynamo export. Yeah, I'm remembering that now because I had a major like issue with that. Not necessarily with Dynamo export, but that was a way that I that was kind of the hard way that I learned that if you're trying to upgrade your PyTorch version or update your PyTorch version, uh, first of all, I looked it up online, and most people were just they were suggesting uninstalling PyTorch and then reinstalling it. So when you reinstall it, then it's gonna come with the updated version. The problem is PyTorch is fucking massive, dude. Like uninstalling it is fine, but reinstalling it isn't like some 5 minute task. It takes a while. And if you're running on older hardware, it takes a while. So here's how I learned the hard way that if you're installing PyTorch or reinstalling, I should say, PyTorch, you need to also reinstall Torch Vision and Torch Audio. Because here's what happened, right? I was trying to get the latest version of PyTorch so that I could use Dynamo export because the old version that I was using, it didn't have support for Dynamo export. So I had to install a new version. But because I didn't know that you had to because I didn't know that you have to install Torch Vision and Torch Audio as well, I uninstalled just PyTorch. So I only uninstalled Torch and I didn't uninstall Torch Vision and Torch Audio. So I still had the old versions of Torch Vision and Torch Audio. And when I later tried to reinstall PyTorch, Torch Vision and Torch Audio, because when you go to the PyTorch website and you're looking for installation instructions, it tells you to install all three of these. So like me, without thinking about the versions and without considering the fact that I hadn't uninstalled those other two, I just ran the entire thing as it is. Right. So I still had the old PyTorch. I still had the old, not PyTorch, the old Torch Vision and Torch Audio versions. And I tried to install the new version of PyTorch. It did that, and I also tried to install the new version of Torch Vision and Torch Audio. So what happened is it downloaded the entire new version of PyTorch and it installed that, which took like a good 1 or 2 hours. And then when time came to install Torch Vision and Torch Audio, it found the old versions. And so because of that, it installed the old version. It downloaded again and installed the old version of PyTorch. And so I had to wait for a long time only to find out that I still have old versions. And so then I had to like remove the entire thing and install it properly, and then I got it to work. But yeah, that's how I remember that. Yes, Dynamo export is definitely a thing, and it's from what I've seen, it's kind of they're kind of they're kind of encouraging the usage of Dynamo export instead of Torch script. There are like usage. There are differences in the way that the neural networks get stored and handled in each of these methods. Okay, so to save and load, you know what? Okay, actually, I can load up. Um, it should mention it here, I think, in the save and load section. I think it should mention it. Was it mentioned here or okay? This approach uses Python pickle module when serializing the model. Thus, it relies on the actual class definition to be available when loading the model. Okay, saving and loading general checkpoints. Okay, when it comes to saving models, there are three core functions to be familiar with. torch.save, torch.load, and this. Okay. So these require you to have the definition, the model definition already present there. So these are not going to work. I'm trying to find the thing that suggested using Dynamo export. I could just look it up instead of hoping that the tutorial is gonna give it to me. Dynamo export. Oh, that was for ONNX. That explains why it's not showing it here. Okay, okay, that was for ONNX. Though I think even the PyTorch version was for, wait, no, is that this is the ONNX this is the Torch Dynamo based ONNX exporter. Isn't there like a, oh yeah, I remember. I was so back then what I was trying to do was um I was trying to learn how to export a model in ONNX format. I just remembered that because I wanted to be able to load it up in there was a platform online that you can load ONNX models onto, and it kind of creates a graph representation of the entire model. I forgot what it was called. Netron, Neuron, something like that. Let me look that up. Actually, I need to go check on my food real quick, so I'll be back. Okay, so yeah, we can carry on. So this was to do with the ONNX format, right? I'm trying to see if there's like a different way to export the entire model. Okay, it says torch script. So okay, I also wonder if we can use Dynamo export without torch script at all. Wait, that doesn't make sense. The whole idea with using Dynamo export is to not use torch script. Why did I just say that? I don't know. Um, what was I trying to say there? I want to see if there's a way to use Dynamo export without trying to export it to ONNX. That's what I was trying to say. Okay. Um, I want to see if there's a way to export using Dynamo export without exporting to ONNX, and more importantly, is there a way to export a model to a different or to a format without using Torch script? Though I feel like if we are trying to use Torch script, it'll be there might be more support. Though I think there were some like drawbacks of using Torch script as opposed to something like Dynamo script or Dynamo export. Yeah, Dynamo export. Okay. You can use PyTorch's Torch script. Here's how it works. Torch script is a way to serialize Torch script is a way to serialize Python models into a format that can be loaded and executed without needing the original model class definition. This makes it highly portable and suitable for deployment in various environments. Tracing or scripting the model. You can either trace or script your model to convert it to the Torch script format. Tracing involves running the model with a dummy input to capture the computational graph. Okay. Scripting involves using the torch.jit.script function to compile the model into Torch script. Okay, loading the model. To load the model saved in Torch script format, you do not need the original model class definition. Sorry, zoned out. Okay, you do not need the original model class definition. Um, so you can load the model and then set it to evaluation mode. Okay, all right. Advantages: portability. Uh, the model can be loaded in the model can be loaded and used in any Python environment without needing the original model class definition. And hermetic export. TorchScript ensures that the entire model, including its structure and parameters, is exported in a self-contained format. Okay. I'm wondering, are there any potential drawbacks of exporting the model using Torch script? Okay, so there's a fair bit of information here. Exporting a PyTorch model using Torch script can be beneficial for deployment and inference, but it also comes with several potential drawbacks and limitations. Maintenance and support. Torch script in maintenance mode. As of recent updates, Torch script is now in maintenance mode, and it is not recommended to depend on it for new projects. Instead, PyTorch is shifting focus to other technologies like Torch Dynamo. Okay, cool. Torch Dynamo. So we're going to go back to that real quick because this is talking about, wait, let's try searching again. Dynamo. Dynamo deep dive, Dynamo overview, read torch.compiler. Okay. What I'm trying to find out is, are we limited to just ONNX, or is ONNX just one of the features that um, Torch Dynamo provides? Like, you can also just export it to a PyTorch related format. Now this is going too deep into the internal workings, and I'm not looking for that. ONNX, okay. Okay. Oh, hold on. Technologies like Torch Dynamo and Torch.compile. Right, so it mentioned Torch.compile here. Where was the search? Here. Okay. So let's open up Dynamo overview and Torch.compiler. Okay. This is a namespace through which some of the internal compiler methods are surfaced for user consumption. The main function and feature in this namespace is torch.compile. Torch.compile is a Python function introduced in PyTorch 2 that aims to solve the problem of accurate graph capturing in PyTorch and ultimately enables software engineers to run their PyTorch programs faster. Torch.compile is written in Python and it marks the transition from PyTorch what? The transition of PyTorch from C++ to Python. Okay. All right. Torch.compile. Torch.compile. Okay. Okay. Okay, so torch.compile has different backends that you can use. And one of the backends is ONNX. So it can then run in the ONNX runtime. And there's also inference only backends. That's interesting. So this is for like when the model is trained and you're ready to just distribute it. Uh, so people won't necessarily be training or fine tuning it. They'll just be using it. Okay, you know what? So torch.compile is probably what we are looking for. Okay. All right. Wait, which one did it focus on? Right. Okay. So we can step away from Torch script. Let's talk about Torch, Dynamo, and Torch.compile. Okay. Also, where was it? So what are we looking at here? Okay, this is torch.compiler. Okay. This is Dynamo. So it doesn't mention only ONNX, right? So I'm just guessing that ONNX is one of the features. ONNX exporting to ONNX is one of the possibilities. It's not the only possibility. All right, let's read what Llama said here. Torch Dynamo and Torch.compile are significant advancements in PyTorch designed to optimize and accelerate the execution of PyTorch models. Here's a detailed overview of these technologies. Torch Dynamo is a JIT compiler for PyTorch that aims to optimize and accelerate the execution of so and so. Okay. It intercepts Python code, analyzes it, and compiles it into an efficient machine code at runtime. This approach addresses the challenges of optimizing dynamic computational graphs, which are common in PyTorch due to its imperative execution model. Okay, Torch.compile is the API interface for using Torch Dynamo and other compilation backends. Oh, okay, yeah. I forgot. Dude, as I was reading all of this, I kept asking myself, okay, what is the difference between like Torch.compile and Torch Dynamo? And then I like just now I remembered, but what I seem to have forgotten was, why did I load this up? Where did this come from? But okay, what I seem to have forgotten was when it mentioned. Actually, no, it didn't mention it here. It mentioned ONNX. Did it mention Torch Dynamo? Holy shit! So what I thought I was remembering was wrong. Where? Okay, where exactly does it mention Dynamo here? This is for using Torch Dynamo and other compilation backends in PyTorch. It provides a simple way to compile PyTorch models into optimized forms. To use so and so, you wrap your model or function with the torch.compile call. Torch.compile. Oh, okay. All right. Specifying the backend if necessary. The This compiles the my module instance using the default backend, which could be Torch Inductor or any other optimized backends. Torch Inductor, PyTorch XLA. Uh, okay, okay. So Inductor is a common backend used with Torch.compile. It optimizes the captured FX graphs produced by Torch Dynamo into efficient machine code. Hold on. So Torch Inductor. Wait, I'm confused about what's. Uh, I'm confused. Wait. Should we read the entire thing? Okay. I'm confused. Is Torch.compile using Torch Dynamo or Torch Inductor or both somehow? Okay, torch.compile in PyTorch 2 leverages both Torch Dynamo and Torch Inductor, among other components, to optimize and accelerate the execution of PyTorch models. Here's how they work together. Torch Dynamo, it it does dynamic graph capture. Torch Dynamo is a JIT compiler that captures the dynamic computational graphs of PyTorch models during execution. It intercepts Python code, analyzes it, and compiles it into efficient machine code at runtime. This is crucial for handling dynamic control flow and input dependent shapes. Torch Inductor, right? Okay, so Dynamo is capturing the code and constructing some kind of graph and then compiling it to machine code, isn't it? Yeah, I think so. I think that that makes sense, right? It captures, yeah, it mentions it here. It captures the dynamic computational graphs of PyTorch models during execution. Okay, and then it converts it to efficient machine code at, well, that's during runtime. This is crucial for, all right, cool. Compilation backend. Torch Inductor is a compilation backend that takes the FX graphs generated by Torch Dynamo and compiles them into optimized C++ or Triton models. Triton? I'm not sure how that's supposed to be pronounced. Either way, uh, kernels, not models. Kernels. This step translates This step translates the captured graphs into highly optimized machine code, which can be executed efficiently on various hardware platforms. Okay, all right, cool. So they work together. All right, cool, cool. So that solved that doubt that I had, that cleared up the doubt. Great. Okay, so I am gonna need to carry on with this. I'm gonna need to reconstruct this whole thing because I still need to do my silly experiments for. I need to stop calling it silly. They're just my fun experiments that I do, in order to kind of get a better understanding of how things work. And I definitely need to do that with neural networks. I'm gonna need to experiment with different types of architectures and different values that I'm passing into them. I want to be able to um, visualize the model learning a relationship. I guess that's the best way that I can put it. I need to see how exactly I'm gonna visualize that. I don't know yet. Um, I'm I guess what I can do is I can run through this section again, the build model thing. I already know most of the stuff that's been explained in the other sections, but I'll still go through it for the sake of refreshing my knowledge. And then I'm going to need to go through the autograd thing again for training, to train the model. After I've done that, after I refresh my knowledge on that, then I can start experimenting with different types of values. Initially, what I want to try and do is I want to try and map. Uh, this is okay. So I feel like I'm going to be doing this with multiple different things because I found myself doing the same thing with linear regression as well. I wanted to try and map a set of values to an output, so a set of inputs to an output. Uh, Basically, trying to show that you could use a linear regression model to to how do I say this? To represent, or you can use a model's weights rather to represent a relationship between inputs and outputs. Because in the case of a linear regression model, what you're saving is the weights. You're not saving anything else. You don't really need to save a model in that case because everything has already been done, in terms of calculation. Once the weights are calculated, all you're saving is well, you're saving the weights in this case. I don't know if there's biases. That's why I stopped for a second there. I was like, because in with linear regression, you get, so you know how when you're calculating a line, you do y equals xm plus b or mx plus b. So when you calculate your what do they coefficients? Yes, they call them coefficients and slopes, or well, one slope. So those are essentially the weights of the linear regression model. It's the coefficients and the slope. And you can then use that to draw a line, because given an x value and the coefficient and the slope, you're then going to be able to construct an entire line on the graph. Because using that, you would be able to calculate your y, and you already have your x. So just like that, you're going to have your entire line. So using the coefficients and the slope, you are able to represent an entire data set's relationship. Though I want to see to what extent this works. That's an experiment that I wanted to do. I haven't done that yet, but that's an experiment that I want to do. Give me a second here. Um, all right. Okay. So here's what we're going to do. Okay. I need to go and check up on my food. Um, but after that, I'm also going to be eating. So I think I'm going to end the stream here. Do stick around. I'm going to raid this person, and then I'll also tell them that I have to go check up on my food. Um, but yeah, that's going to be it for today's stream. Cutane, thanks for hanging out. Thanks for stopping by and lurking. Anyone else who might have been lurking in the chat, thanks for hanging out. I'll try to stream again tomorrow. I'm going to carry on with this. Hopefully, I'll finish both of these sections today, because I just need to like refresh my knowledge on them, and then I'll be able to start doing some interesting things with feed forward neural networks and trying out different feed forward neural network architectures and stuff like that. Okay, so I'm gonna leave now. Um, I'm gonna raid, and yeah, I hope you guys have a nice day, and I'll see you all next time. Peace.